I'm going to talk a little bit, but not the whole hour, so I'll talk as much as you want, or as much as you want. You can ask me questions or about anything, which I may or may not answer. So I guess this is mostly freshmen and beginning students in physics, right? Yeah, I began physics in Berkeley, so University of California. I started as an engineering major, actually, and changed into physics after one semester there, liking physics about 10 times more than I liked engineering. Maybe it was a reflection of the way engineering was taught. Can you hear me in the back? Maybe it was a reflection of the way engineering was taught in Berkeley a little bit, because as a freshman in engineering, I had 2 courses. One of them was engineering drafting, and my teaching assistant didn't like my arrowheads very much, and so that didn't go very well. The second class was surveying. We're using a transit to measure the heights of buildings and so forth, which was fun for about an hour, and then it was boring. And in physics, they were discovering lots of the new elementary particles in Berkeley at the time I was a student. And so I got captured by all that, and ended up, as an undergraduate, working up at the Lawrence Berkeley Radiation Laboratory on the accelerators themselves, because as a student, I didn't know enough to do the physics. That I've ended up working as a skill that I've kept my whole life. So I've most recently been worked on the design of the next big particle accelerator that's supposed to follow the one in Geneva, scattering electrons on positrons instead of protons on protons. So, you can learn skills at a young age that end up being a big part of your career. Anyway, I went into particle physics and did a lot of particle physics experiments on big accelerators and in other ways, but I've worked on the big accelerator, linear accelerator at Stanford, the big accelerator in Fermilab, which is the biggest one in the US, and at Brookhaven at one time, which is in New York, and at CERN, where they now have the biggest accelerator in the world. I've also done particle physics not using accelerators. And as an example, I may have gotten a Nobel Prize for making a discovery that took me 22 years. But I also spent 10 years of my life looking for the single magnetic pole, magnetic monopole. Electric charges come in plus and minus. And there's single ones, and you walk across a room and you touch a doorknob and you get a shock, right? And we have 4 equations, which you probably haven't quite seen yet, called Maxwell's equations, that describe electricity and magnetism. And they're completely symmetrical, except the letters are different for magnetism than electricity, except for one difference. One equation has a little q for charge on one side, or rho, and the equivalent one for magnetism has a 0. But we all know that physics is usually quite symmetrical, so it's been a goal of physicists for 150 years since Maxwell's equations were brought forward to find the magnetic equivalent of the single magnetic pole. In fact, even earlier than that, people looked at magnets that were just found in nature. You cut them in half and they still have a north pole and south pole. So that isn't the way to find a single one, or you try to isolate them. And in about 20 years ago or so, I was teaching in a school for advanced, like PhDs, people that were PhDs already that were advanced students. You're a student your whole life. It's just if you do physics. And it was in Scotland. And in Scotland, it was in the famous place, the St. Andrews Golf Course, which is the most famous golf course in the world. And the dorm for the school, it overlooks the 18th hole. The dorm isn't very fancy, but you're in a fancy place. So when I was there, I was teaching, they had 4 lecturers, and you taught one day, and the next day you were off, and the next day you taught, the next day you were off. And the day that I lectured, the lecturer before me is now, he wasn't then, but he is now a very famous theoretical physicist named Gerard 't Hooft, a Dutch physicist. And he was working on another goal that physicists have had forever, almost ever since Einstein, which is to find some way to unify all of physics back together. Einstein tried to unify gravity with electricity and magnetism, and it didn't succeed. So Hooft tried to understand the problem by backing off from it and looking at the mathematics, and he realized that if the mathematics that's used in a grand unified theory is the same mathematics that we use to do quantum physics and other areas of physics, which has got a fancy name, non-abelian gauge theories, then there were certain features that were just inherent in it. And one of them was there is a magnetic monopole. But the magnetic monopole has the scale of where these different forces, the force that binds us together called the strong force, the gravitational force, the electric force, and the weak force, which causes radioactive decay. We have 4 forces in nature. So supposedly they come together somewhere, but it's at a very high energy. And what de Hooft was, when he was lecturing, realized was that, or said, was that the scale of grand unification set the scale of these single magnetic poles. So I was sitting like you are, in an audience, didn't have any books, no library or anything. We're off on a golf course. And I had always been interested in the mystery of where the magnetic monopole was, so I was familiar in my head with how people had looked for them. Maybe not all of the ways, but a lot of the ways. For example, one of the first, maybe the only really good physics experiment done with moon rocks when they came back was to look for magnetic monopoles, because the idea was that the moon is unshielded, monopoles come in, a lot of them just over the centuries have collected in this moon rock, and you have a big density of them to collect, and you put a loop around it and see if there's magnetic monopoles. So, so that experiment, or experiments on the accelerators that I knew about, are limited by the mass of this particle. And what I realized sitting in the audience was that the mass of all the searches that had previously been done for a century and a half, as far as I could remember them, when I went back and looked in the library, it was true, all made a tacit assumption that nobody kind of recognized, which is that the monopole has the same kind of mass, more or less the same mass as other elementary particles, the proton or other particles, which is 10 to the 15 times less than the unification mass. So if the mass of these monopoles was extremely heavy, you couldn't make them on a particle accelerator. They weren't high enough energy. They didn't stick in a moon rock. They'd go right through the moon because they had so much momentum, so much energy to have. So you had to invent a new way to do that. And so I came home and got a few students. We developed a way to do that. I spent 10 years of my life looking. We didn't see any. So that's kind of how physics goes. Anyway, I'll tell you for a few minutes, and then people should interrupt me as much as you can. Don't be quiet. A little bit about gravitational waves. And if you look at this first picture, it's a picture of the sun and the earth. Only look below it. What I've done is draw below it a grid. And that grid is meant to, you can think of it as a trampoline. It's a two-dimensional representation of a space. And in this two-dimensional representation, you'll notice that underneath the sun is a big distortion of a flat area. And underneath the earth, if you can see it, there's a little distortion as well. It's not, the lights are a little bright, so you can't see it too well. But this is then Einstein's idea about gravity. So if we go back, we all learned gravity. I did, you did, somewhere when you're about this big, from a teacher that told you all about why the apple, how the apple falls out of the tree. And eventually you got to high school or somewhere and you learned that Newton had developed a theory of gravity. And his theory of gravity was that the two objects will attract each other inversely proportional to how far apart they are, squared, and proportional to the masses of the two objects, product of the masses of the two objects and some constant in between. And so that was Newton's theory. Your teacher in school told you that when you jump, the Earth pulls you down. That's the formula. And did anyone in the school ever ask their teacher why the Earth pulls you down? When you heard that story, you all heard that story because that's how it's taught. Did anyone think or question why the Earth pulls? You did? Yeah. So what was the answer? They didn't give an answer. Okay. Anybody else ever think that, okay, you're told the Earth pulls you down, but why? That, as a physicist, that's what you have to do, is ask the next question. So anyway, Newton didn't have an answer. He wrote down an equation which worked for the moon going around the Earth, or the Earth around the sun, or even describing the tides, or the apple falling out of the tree. And it's this famous formula. He called his theory the unified theory of gravity. Unified because you could use it for the apple falling out of the tree or the Earth going around the sun. It's all the same. He didn't describe why. So that's the first problem with Newton's theory. Newton's theory, by the way, is the most successful theory of physics ever. So I'm not criticizing it as being flawed. It's the way physics progresses. We basically have a theory. It describes almost everything. It doesn't do everything, and then you have to modify it. In this case, Einstein came along 100 and some years later and modified Newton's theory with this picture here. And what was the problem and the reason? Nothing was wrong that had been seen with Einstein's theory of gravity. It basically worked for the planets, it worked for the tides, it works for the apple, but it doesn't describe why, and as physicists we have to describe why. And it has a second problem, which is more practical, and I mean it's intellectually important to know why, but maybe you just didn't have the explanation with the formulas right. And the second problem is that when the apple falls out of the tree, for Newton, you see it right away. We call that instantaneous, we have a fancy name, instantaneous action at a distance. That is where it's, so for the apple falling out of the tree, it doesn't matter at all. But when you talk about something like, I'll talk about something that happens in a distant universe, or let's say the sun, which I'm talking about here. If the sun were to burn out right now, we wouldn't know it for 7 seconds, the time it takes light to go from the sun to us. But in Newton's theory of gravity, the gravitation, whatever is gravitational, we would know immediately, no matter where it happened in the universe. And even Newton realized that that wasn't right. He didn't know how to explain it, but he wrote down all this stuff in a book called the Principia. And that book was very important for more than just theory of gravity. It's also where he wrote down the scientific method, which we all use. And I wish some more citizens would use, because maybe they'd understand what fake news really is. Well, it is. A way to look isn't to say who said something, but to understand what you know that's true or not true. I think if our citizenship understood the scientific method, even at an elementary level, we wouldn't have as much trouble with alternate news and fake news and all this kind of stuff. Anyway, so this picture here is Einstein's answer non-mathematically. What happens is that any massive object in space distorts the space and the time around it. So this is a picture of two-dimensional of the distortion of the space because the sun is sitting there. You might think of a trampoline. So if I have a trampoline and I put a bowling ball on it, it'll go and be different. If I have a trampoline with nothing on it and I put a marble on it, it's not going to go anywhere. But if I put a big bowling ball in the middle, the marble will roll toward the bowling ball. That's the idea here. So the Earth is being pulled toward the sun because there's a big well or a distortion of the space. I'm going to make this problem harder for you in just a second. And so it's pulled toward it, but the fact that it's trying to go around the sideways, it develops what we call centripetal force, which counters it, and so it stays in an orbit that goes around it. If it were standing still, it would fall toward the sun. Now the complication, which I'll just say so you hear the words, you don't have to worry about it for the rest of the lecture. Every point that's on this grid here is not just two-dimensionally disturbed like I showed it here, but four-dimensionally disturbed. It's first, I can't draw it. It's disturbed in space, but also time. So time gets affected on every square just by the presence of a mass near it. The fact that it makes these distortions is used by all of you. It's called the theory of general relativity. It's very complicated because of the fact that it's four-dimensional. It's space and time together. You not only won't learn it as in the freshman year, you won't learn it as undergraduates, and usually it's almost the last course that students take in graduate school, and many of them don't take it because it's too hard. And that's because the mathematics in four dimensions of space-time is incredibly difficult to do. You end up getting infinities and all kinds of things artificially. So anyway, he formed this four-dimensional space-time, and it has the function of physically having the distortions that I point out here. So that solves the problem of why. He also solved the problem of the transmission of the signal. So it's not instantaneous information at a distance, action at a distance. Instead, in his theory, it all travels the same as his theory of special relativity, that is at the velocity of light. So that when I show you a little bit of data, you'll see that we rely on the fact that what we see actually happened a long time ago, and it's taken time for the signal to get to us. So these two conceptual problems were what was contributed by Einstein, and he then brought forward the theory of general relativity, which is our theory of gravity. The biggest puzzle in physics, the biggest problem we have is this is a fantastic theory. I'm just going to show you a little corner of it. And we have a second fantastic theory in physics, which is quantum physics, basically, or quantum field theory, that describes essentially everything that happens when you go to a great big accelerator and you smash these, almost everything, smash these particles together, and you can tell who interacts with whom, or its strength, and everything about it. So we have two theories of physics, and we don't know how to bring them together. It's the biggest puzzle in physics. It's crazy to have a field called physics, but we have two theories, not one. So it's the biggest ultimate problem that we have. Let me talk just a little bit, and then I'm not going to lecture. So my comment here is what I've shown is three experiments as symbolically. This experiment here is the experiment at the Large Accelerator in Geneva, and the discovery of what's called the Higgs Boson. The Higgs Boson describes for us for the first time where mass comes from. Why do we have any mass at all? We used to have a theory of particle physics, which was pretty good. We call it the Standard Model, and it fits almost everything we know, but it didn't really explain mass. So mass is described by this Higgs boson. The experiment, the theorist that proposed the theory about 60 years ago, and another theorist won the Nobel Prize for this in 2013. In 2015, in another high-tech big experiment in Japan and in Canada, two places, not quite the same experiment, they discovered that neutrinos, our smallest and most kind of elusive particle, actually has the ability to transform itself going through space from one kind of neutrino to another kind, what we call neutrino oscillations. It comes about, I can't explain to you simply why, because the neutrinos are not zero mass either. They have a little teeny bit of mass, and they're different from each other. And that was proven in this experiment here. And then our experiment saw what I'll show you, which is gravitational waves. My main point here is that there's something you can glean from this. Modern physics is very high tech. These experiments are huge, very different technologies, but they're huge. There are large groups of people involved to carry them out, and they're multiple years. And there's a huge amount of varied technology, from the most advanced computing you'll find anywhere in the world, to the fastest circuitry, to incredibly sensitive instruments that are used to either sense the particles or, in our case, the light that's traveling in our apparatus and so forth. So physics is transformed. What that's done, in my mind, is make it very different than when I went into physics, and a much better opportunity. So what do I mean by that? When I went into physics, if you wanted to attack a new physics problem, like is there a magnetic monopole, when I did that, my point isn't whether we found it or not, but I had to invent everything that had to do with that experiment, other than some standard electronics and so forth that existed. So my colleagues and me. And so in order to do physics, you had to have first a good idea. Secondly, you had to do a heck of a lot of innovative work to develop the instrumentation. We now live in an age where instrumentation has changed incredibly quickly. I mean, you just have to look at these things and ask what's in them. And this has everything in it from general relativity, believe it or not, when you do use GPS, to very high resolution screens, to computing, to telecommunications, and blah, blah, blah. So, and this didn't exist, what, 15 years ago? So technology has changed really fast. So the problem for you, which is different than it was for me when I started out in physics, is how to take this incredible amount of technology and apply it to some basic science problem, if you're in physics problem, that we haven't been able to do before because we didn't have the tools to do it. So now we have many more tools, and there's many opportunities, I think, to apply those tools to the most important problems that exist. So you're better off than I was when I started, and we had to build all this stuff. Anyway, let me keep going just a little bit. So I warn you that what we saw took some time to travel. And so this is what we saw. My story begins 1.3 billion years ago. Newton could have never told us that. He would have thought what we saw happened right now. But we know that what happened that we detected started 1.3 billion years ago, and it was transported, the signal, which we finally detected, was transported to the Earth at the speed of light for 1.3 billion years, and it got to us. If you're at the edge of the universe, it's about 15 billion years. So we're 10% out to the edge of the universe, more or less. So it's not way at the end. There could be things further away. And that took 1.3 billion years to get to us. And then we, in the meantime, built an apparatus that was able to see it. What the picture is two black holes. And it's not an artist's animation. It's a computer rendition from our data, which I'll show it to you in a movie in a second. This is just to convince you that the equations are complicated. This is the four-dimensional equivalent equation from Einstein that's like the m1, m2 over r squared formula of Newton. So going into four-dimensional space-time, you get some complicated formula, which of course I'm not going to explain to you now. And that's what you have to deal with. Okay, so Einstein then wrote a paper. He did this in 1915. And in 1916, he wrote a paper. And again, it's illustrative how he got what he did in this paper. It's a lousy paper, but he was still a genius. So in 1915, he had his new theory of gravity, theory of general relativity. And most theorists didn't jump up and down and believe it. First, they couldn't understand it. And secondly, the World War I was going on. It was kind of a complicated time. Anyway, the next year, he looked at the theory, and he didn't derive from, and why I say it's a lousy paper for two reasons. One is he didn't derive anything. He just looked at it, and he formulated a form of the equations that looked, with different letters, of course, a lot like the equations you get in electrodynamics, electricity and magnetism. And he didn't derive it from the basic theory that I showed you, the complicated theory. He just kind of looked at a way to form the equations. And so he made the leap, which is what he was great at. kind of intuitively, he made the leap that if the equations have the same kind of form as electricity and magnetism, and in electricity and magnetism we have electricity, we have magnetism, and we have electromagnetic waves. Light waves that we're seeing right now, radio waves, microwaves, every kind of wave we use for tools, we use for astronomy, and so forth and so on. So if there's waves associated with electricity and magnetism, and the equations have a similarity to the equations of general relativity, then he hypothesized there must be gravitational waves. And he wrote this little paper with nothing derived and made mistakes. There's a mistake of a factor of 2 in it, which would be deadly for us when we did the measurement if we tried to interpret it. So people can write a lousy paper which ends up being monumental, actually, because he had a great idea, which he had in this paper. So that was the beginning. 1916, he proposed that there were such a thing as gravitational waves. We then as a physicist, if you're an experimental physicist, you want to make an experiment, if you're trying to test something new, where you can control all the variables so you don't fool yourself. So you want to make something and that's what was done for electromagnetic waves. So the way electromagnetic waves were proven is Maxwell developed the equations of electricity and magnetism in the 1870s, I guess. And then in 1880 something, a physicist named Hertz took on the task of trying to see if there were electromagnetic waves. Anybody know how you make an electromagnetic wave? Okay, you take a charge, 2 charges, excuse me. You take 2 charges and you oscillate them like this, and that makes a wave. Okay? It's called a, excuse me, it's called a dipole. So you may have in one room, you do this, you go in the next room and make a little radio receiver, and you receive the electromagnetic waves. And then he moved it forward and backward, and so it was wave-like. And that's the way we had the proof from Hertz that there were electromagnetic waves. So you'd like to do the same thing to see if there are gravitational waves. You'd like to make a source, the equivalent of this, for gravitational waves, make a detector, move it forward and backward, and show that it has signals and that they're wave-like. That turns out to be absolutely impossible. And I don't have the time to go through with you. So we're forced into a situation where instead we have to rely on nature to give us a strong enough signal so we can detect it. In our case, we were really lucky because the thing that nature gave us to give us a signal was so interesting that we became famous for it. So we got lucky, kind of. And that's these black hole collisions. So what's a black hole? So a black hole, let's just define that. Then I'll just show you quickly the data, then I'm going to stop. So a black hole, everybody's heard the word black hole. You've all seen it in the newspapers. There's different black holes, and they're complicated mathematically, but it's easy to think what they are conceptually. Conceptually, it's the following, that if you take a region of space where gravity is so strong that nothing can get out, not including light, because light bends in Einstein's theory, so nothing can get out, it's trapped, then obviously it looks black. Nothing gets out. That's what's a black hole. And in nature, we can get black holes from something physical. They happen from, for example, the death of a star, what we call a supernova. So at the time a star dies, it actually collapses into something that's highly dense and has a huge amount of gravitational pull. And if it's enough, it becomes a black hole. Our sun won't. Our sun will eventually die, long after you, but it'll eventually die. And when it does, it'll collapse, but it's not big enough to actually make black holes. To make black holes, you need a star that's maybe 3 times, or more than that, more than our sun. But so that's what a black hole is. It's a region of space. And so the ones that we've seen came, we think, from very heavy stars, maybe 30 or 50 times the mass of our sun, that decayed and that burned out and then gave a product, which is a black hole. So let me put it on a scale. So this is Riverside, a Google map. This is Riverside and Los Angeles, okay? What we saw is shown here. Two black holes, notice here and here. This is how heavy they are. One's 29 times the mass of the sun. The other's 36 times the mass of the sun. So each of those is 30 times the mass of the sun. That's 10 million times the mass of the Earth, okay? Crowded in a space not much bigger than Riverside. And separated from a second one going around each other, which is at about the center of Los Angeles. And they're going around each other at about half the speed of light. So that's the unbelievable thing that we detected. As they go around each other, they radiate what I call gravitational waves, which is what we detected, lose energy doing that, and they eventually come in and collide. And we can trace that from the signals we detected, and that's shown in this picture here. So this is from the real data of the two gravitational waves superposed on the universe. They're going around each other, they're losing energy, they're obviously interacting with everything around them. They're losing energy to each other, so they're falling in toward each other. They eventually come together, and they make one bigger black hole. In the meantime, they've radiated away a fair amount of energy into gravitational waves. If you notice, I had on the first, one of them was 29 solar masses, 29 times the mass of the sun. The other one, 32. The final was 3 solar masses, less than the sum of those two, and that was what radiated away into gravitational radiation. So the rest of the picture is shown here. As they're coming together, they're radiating away gravitational radiation. And that radiation propagated through the universe for 1.3 billion years while we got smart enough to detect it. By the way, 1.3 billion years ago on Earth, we were just transforming from single cell to multi-cell life. So that's kind of when this started. When it comes to the Earth, it distorts space and time, and I've exaggerated a little bit in this picture, and so we see the distortion of the Earth. And we made an instrument, which I don't have time to talk about today, that was capable of seeing this small distortion. So I think that's probably as much as I'd like to do, so people can ask me things. This is a picture of the instruments. We have two, one in Hanford, Washington, one in Livingston, Louisiana. I'll show you the signal. This is then what happened on September 14th, 2015. That's the discovery. This is the region in the southern hemisphere that we know this gravitational wave signal came up from these two black holes through that region. We get that by, what did I do? We get that by reconstructing when it was seen in the state of Washington and when it was seen in Louisiana. It was seen first in Louisiana. And so we can reconstruct it. These are the signals. And these signals are raw. Usually when you see physics experiments, they'll show you the data, and the data's been through lots of computers and changing it and so forth. And you rarely have an experiment where you can just show the raw data. This is essentially the raw data. So what's shown is time going this way. It's about 0.2 of a second. And the size of the distortion, when I showed the distortion of the Earth, the size of the distortion in units of 10 to the minus 21, a very small number that we were able to detect, but I don't have time to tell you how. And the signal, you'll notice, gets a little bigger, and it's just a bunch of wiggles to you. But those wiggles are important, as I'll show you. So then 7 milliseconds later, we saw another one. And you'll see the first qualitative view is that they look alike. This is in 2 instruments, 2/3 of the way across the US. And just looking at the data, nothing's been done to the data except to remove the frequencies that are outside of the frequencies that we look at. So it's just what we call bandpassed. And that's the 2. They almost look alike. And now I'll draw a curve through them, which you can barely see. That line, if you can see it, if you can't see it, you know why you can't see it, because it looks so much like the data, is the calculated line of Einstein's theory of general relativity for those two black holes to collide. So you can see that. I'll end by just saying I was walking down Madison Avenue in New York. This is the fancy street with fancy stores and boutiques and all that stuff. And I was with my wife. It was vacation. This is a year ago. And I look in a window, and there's this on a bunch of dresses. And I went in the store. This is the store so fancy they can't just open the door. You have to knock, and they come and let you in. And I went in the store, and I asked where they got that. And they told me the name of the designer, who happened to live in Los Angeles. So when I came back, I contacted this designer. And she had made this series of dresses and things with this on it because she thought it looked, artistic. Of course, it's scientific, not artistic. I couldn't convince her. And then, so she ended up making ties with this signal on it for us that I wore at the Nobel. Yeah. So I'll end there. So somebody should feel comfortable enough to ask me a really good question, or a bad one. I don't care. Yeah.
I was wondering how you kind of answered a little bit of the question, like how did you know it was the two black holes spinning? But how did you come up with the predicted data with the two black holes spinning?
Good question. So one of the reasons it took 100 years to test this is that we had to make very fancy instruments. The other reason is that we have to calculate Einstein's equations for all different conditions, because you don't know what black holes, what they're spinning, how far apart they are, what masses they have. And so it's impossible to do that without using computers. If you did it by hand, you'd need armies of people to do these really difficult calculations. And it turns out that's not, just like it's hard for people to calculate it, we call it numerical relativity. So general relativity is the general problem. Numerical relativity, if you see the words, is doing it on a computer. People worked on, the National Science Foundation even made a challenge to try to get people to do it while we were starting to build LIGO. That failed, nobody did it. There's a guy finally that learned how to do it. He was good at computer science and physics at the same time, in about 2006. So by the time then that people could make the calculations, it was maybe 2011 or 2012. Just in time for us. We needed them in 2014 when we made the, so it turns out it's subtle why it's so hard on a computer, but you can imagine having looked at what goes on here. Well, that's why we take every piece of data that looks like this. It, of course, all doesn't look like that, it's just noise. And we compare it with 300,000 templates of all the spins and different masses they might have and orientations. And we try to cover the whole complete space and see if there's any matches. And we just slide it along the data. So it's a huge computing problem. More questions, comments? Back there. Loud.
Earlier, you showed something that said it happened 1.3 billion years ago. And I guess my question was, is it assumed or do we know for sure that gravity propagates in this way?
Good. Thanks. That's a good question. So the 1.3 billion years ago assumes that Einstein's right, that there's one speed, it travels at the speed of light. Now we have some experimental information, but I didn't show you. Because black holes, we have no way to test. They're just black holes. And so that was theoretical. But more recently, and I didn't show it today because this isn't a physics seminar, it's introduction, we detected a signal from what are called neutron stars, two neutron stars coming together. And neutron stars are a bunch of nuclear matter. And when they come together and collide, they make light and they make neutrinos, they do make other things. And we saw that signal not as far away as this. It was a little over 100, I think 130 million light years away. And the signal was also seen in a satellite, photons, they didn't see the gravitational signal, they saw a signal from photons, so that's electromagnetic. And it was 2 seconds after ours. So we know to 2 seconds out of 130 million years that it's at the speed of light. it's probably much even, that's small, that's a small difference. And it's probably much smaller than that. We expect the signal from light to come later because the gravitational signal is these things coming together. And the light, the photons come about because of the nuclear interactions that happen after it's together. So we can't calculate because we don't understand it well enough that it should be exactly 2 seconds, but you expect it to be some time later. So it's pretty close proof that it is at the speed of light. But it's true that if you read our paper, the discovery paper, we do make the point that we're assuming it's the speed of light when we say that distance. Yeah.
So what comes after, now that you verified the discovery of gravitation?
Another good question. I mean, I call it a good question if I have a good answer. When you ask me the one I can't answer, then it's a bad question. No, look, the analogy I like to make, it's totally presumptuous, but I'll make it anyway, is to Galileo. So go back in time, 1608, Galileo realized that people had made lenses for glasses for the first time, and he made a telescope to do astronomy. People had made other telescopes, but not to really do astronomy. He made the first telescope to do astronomy. And he looked through the telescope and he looked at Jupiter. So what did he find? Somebody knows. He found that Jupiter has 4 moons. And that was the first discovery of, without just the naked eye, of modern astronomy. Now it's 400 years later. And 400 years later, we know something about the age of the universe, accelerating universes, what kind of stars there are, collapse of stars, supernova, a huge amount of astronomy. All of that is based on things that happen that give electromagnetic signals of one sort or another, whether it's light or gamma rays or microwaves or X-rays or whatever. It all comes from that. Now for the first time, we have a way to look at the sky or the universe that's looking at gravitational effects instead of electromagnetic effects. So we have a whole new science that's open to us. Not that we can all do it immediately. It took 400 years to do it since Galileo. But in the next centuries, and maybe the kind of things you can do, that this has opened a little crack in the door, if you want, of being able to study the universe in a completely different way. And we know that the visible radiation is only a small fraction of what's out there. We have dark matter, we have dark energy. We call it that. And there's going to be transient objects that are different that don't happen to give electromagnetic signals. Black holes are one, but we had those inferred. So I think long after my time, long after your time, this will be a great science. So great question. Yeah. Okay. The question is, how often do 2 black holes merge like this? It's a good question again, because we don't really know yet, because we have to get enough samples to be able to extrapolate how many happen in the whole universe. As I mentioned, we only see 10% of the way out in the universe, so what happens from there out to earlier, and out further is earlier times, so it's a cosmological question. It's one of the interesting questions is how many there are. We've seen, not just this one, we've seen about somewhere between 5 and 10 already. So I think with the improvements that we think we've made in our detector for the next data running, we'll be seeing them at a rate of 1 a week or so. And eventually we'll get a nice distribution of what their masses are, what their distribution in space is, and be able to tell accurately. Now we give a limit. We tell inaccurately, if you want, using extreme models, how many there are in the universe from the small number that we've detected. Yeah.
Your instrument that you use for the LIGO detectors are like super sensitive, right? So how did you combat like the stuff on Earth, all of like the signals and all the crashing? Like how do you know it's not like a storm that's just vibrating the ground of the instrument or something like that?
Okay. So the question for those that heard it or didn't is you're living here on the Earth, you're trying to make this really incredibly sensitive instrument, and a lot of things happen on the Earth. How do you know it wasn't lightning or some other phenomenon on the Earth? The answer is that we first have 2 detectors, not one, separated in space by a long ways. So they're 3,000 kilometers from each other, one in Louisiana, one in Hanford, Washington. If something happens on the Earth, an earthquake, or even thunder or lightning, well, lightning doesn't travel that far, but anything on the Earth that happens, and a lot of things do happen, travel at the speed of sound, not the speed of light. So we require that the 2 instruments, and if you notice, they were the same to within 7 milliseconds of each other. That requires the speed of light for the same signal to get between the 2. That limits quite a bit what it can be. All it can be is something from the sky, something that travels at the speed of light. So we know that within how far apart the signals were, that it required the speed of light. But maybe it's just accidental. Something happened in Louisiana, something else happened in Hanford, and they happen to be in this 10 millisecond bin. How do we tell that it isn't that? And we tell that by comparing off times. We look at Louisiana, but we look 10 milliseconds out of time, 20 milliseconds out of time, 30 milliseconds, 40, and we look at all those possibilities and build up a probability that it's totally accidental. And that turns out to be, the probability, I think, on this first event was that it was probable less than 1 over 370,000 years that we would see something by accident, just by measuring all these bins. More? Do I have time? Or?
A couple more.
Okay. Yeah.
I had a question. Do you still plan to do anything with the magnetic monopoles? A new accelerator being built for jet engine.
Yeah, well, accelerators can't because they're not high enough energy. So these monopoles are so heavy that you need to do it like we did it. We did this more than 20 years ago, and it still stands as the best limit. There are reasons now that we think the number of monopoles that were made in the early universe may be very limited because of the way the early universe developed. So right now there's not a lot of motivation to do better than we did 20 years ago. We were good enough to get to where quite a bit better. We had a kind of fuzzy bound that there couldn't be more monopoles than would short out the magnetic fields that are in the universe, and there are magnetic fields. So in order to do something significant, we had to get below that, and we were below it by a factor of 100. So it's the best limit. If there was good theoretical motivation, somebody might do better. We built a detector about the size of a football field to do this, deep underground. So it was a huge project to do it, and that's why it took 10 years. But we're still stuck with no monopole, to my disappointment. Back there.
Last question.
You talked a little bit about magnetic monopoles and grand unification in the beginning.
Yeah.
I was just wondering if you work with any science that's beyond the standard model kind of stuff.
Yeah, the question is, I talked about grand unification, and another problem is that it has kind of a two-sided thing. Grand unification is the ultimate dream that we have as physicists. The second is that on particle accelerators, we have a very good theoretical framework called the standard model. You might even call it the standard theory that explains almost everything we see on a particle accelerator. And we're trying to look beyond that. We don't have good guidance. We thought we did. There were some ideas that there was a new kind of symmetry in nature called supersymmetry. So far, they haven't seen that. So it could be that we just don't have enough energy in present accelerators to see something, or it might be that we have to look more sensitively. So since we don't have larger accelerators, the program is to look more sensitively at CERN, which is what a set of physicists here at UCR are doing. And the other possibility is that a different accelerator, one that uses electrons and positrons, could give us more sensitivity, looking precisely at some questions that can't be done so easily on the Large Hadron Collider. we have to be patient, unfortunately. Sometimes breakthroughs come very quickly, other ones we have to work out really hard. We know we don't have the ultimate theory. We need more clues to pull it together.